Okay, guys, welcome back. This is going to be part 2 of the 8.2 instructional video. And at this point, you have already gone through 8.2 part 1. If you have not, you must pause the video, go back and watch 8.2 part 1. Okay, this will not make sense if you don't watch 8.2 part 1. So where are we? Well, what we briefly covered to review in 8.2 part 1 was the following. We have two distributions, thinking of the trout example. The whole population, then we took the mean, or then we have all those 100 sample means. We've got the 100 samples, okay? 100 kids caught 5 fish each and found the means of the lengths of their fish. We take those 100 sample means, make a distribution out of them. So you have the population, just the standard, all the fish in the pond distribution, and we have the distribution of all those sample means. And the big idea we discussed in 8.2 part 1 was if the population's normal, there are 3 consequences. Number 1, the distribution of all these sample means will also be normal. Number 2, the mean of the population will equal the mean of all these sample means. And number 3, the standard deviation of all these sample means equals the population standard deviation divided by the square root of your sample size, or n. But what happens if we don't know that the population's normal? What do we do? Well, that's what this second video is all about, and really what our second theorem is all about. Again, what I'm going to have you do is I'm going to have you write to the black arrow. I'm going to write down the symbols that fill in the blanks. You pause the video and write it down, fill in the symbols, then unpause the video and listen to the explanation. Okay, so here is theorem number 2, the central limit theorem. Okay, if you take a college stats class, they're not going to call it theorem 2, they're going to call it the central limit theorem. Incredibly important. If the sample size of the distribution of sample means, okay, so we're talking about not population, distribution of sample means. If the sample size of the distribution of sample means is greater than equal to 30, then the distribution of sample means can assume to be normal, no matter the distribution of the population, and it will have mean mu of x bar and standard deviation sigma of x bar. Here's what it boils down to. If we don't know what's going on with the population, right? If we know it's normal, we apply theorem 1, happy days. But if we don't know what's happening with the population, we can look at the distribution of sample means, and if our sample size is bigger than 30, then the distribution, what do I mean by that distribution? I mean the distribution of sample means can be assumed to be normal. Okay? This guy over here, if the sample size is greater than or equal to 30, can be assumed to be normal. No matter the distribution of the population. Folks, this is the number 1 area where people screw this up. They think, oh, remember, population over here, distribution of sample means over here. They think, oh, the sample size is bigger than 30, so the population's normal. No, do not do that. Pause the video, rewind it 10 seconds, hear me say it again. No, don't do that. Because the sample is bigger than 30 does not mean the population's normal. We don't know what's happening with the population. We don't know. We don't care. Okay? What we know is that if the sample size is bigger than 30, the distribution of sample means is normal. Put it in the context of the trout problem. If instead of catching only 5 fish, that each kid caught 30 fish or more, then we would know that those 100 sample means made a normal distribution. We don't know anything about all the fish in the pond. That doesn't mean all the fish in the pond have a normal distribution, unless we're told that. But if each kid caught more than 30 fish, that distribution of those 100 samples, 100 sample means would be normal. That's the central limit theorem. And of course, those sample mean, the distribution of sample means is going to have a mean mu of x bar and standard deviation sigma of x bar. So what are the consequences? Well, again, let me write the symbols in. You can pause it and write down the definition. Okay, you can go ahead and pause, write those down. Now that you've written them down, what I hope you see is some major parallels to Theorem 1. Some stuff that's almost the same. Now, bullet 1 doesn't really have to do with Theorem 1. That just tells us that the bigger the sample size is, the more normal the curve will get. We know that if the sample size is 30 or larger, yes, we can say it's normal. By it, we mean the distribution of sample means. But if the sample size would be 1,000, it's going to look a heck of a lot more normal than if the sample size is 31. Okay? But nonetheless, as long as the sample size is greater than or equal to 30, the distribution of sample means is normal. Your next two consequences you've already seen in Theorem 1. They're the exact same. The only difference is in the initial setup. Let me explain. If the distribution of sample means let me back up. If the sample size is bigger than 30, according to the central limit theorem, the distribution of sample means is normal, which means your mean for your distribution of sample means, that's m of x bar or mu of x bar, equals your population mean, mu. Okay, remember mu is population. Mu of x bar is your distribution of sample means, or the x bar distribution. Very similar, actually identical to a consequence of Theorem 1. Consequently, your standard deviation of the distribution of sample means equals the population standard deviation divided by the square root of n. Again, same consequence as Theorem 1. Okay? So what's the big picture here? The consequences are identical. What we will have to determine is if by Theorem 1 or by Theorem 2, the central limit theorem, if the distribution of sample means is normal. Okay? If we determine that the distribution of sample means is normal, whether it's by Theorem 1 and the population's normal, or by Theorem 2 and the sample size is greater than or equal to 30, we will be able to determine mu of x bar and sigma of x bar. Okay? Thinking about the initial rainbow trout problem that we solved with a sample size of 5. Would that apply to the central limit theorem? No, it would not. Okay? Because our sample size is not greater than or equal to 30. The initial setup of the trout problem where the kids are only catching 5 fish and finding the mean would mean that we don't have enough of a sample size to determine that the distribution of sample means is normal. We would have to know that the population's normal by Theorem 1 if we wanted to assume the distribution of sample means is normal. So what are we going to do now? You do not need to write these down. What I want you to do is let me write the symbols, talk you through these, and then for 1, 2, and 3, you are going to determine whether the distribution of sample means will be normal by Theorem 1 or Theorem 2. Okay? So let me fill in the symbols, and then we'll solve each one. Okay, so again, what you're doing here is you're using your notes on Theorem 1 and Theorem 2 to determine if the distribution of sample means is normal, not the population. Remember, we can't determine anything about the population. We can only use the central limit theorem and theorem 1 to determine stuff about the distribution of sample means. Okay. So suppose X has a normal distribution with mu equal 18 and standard deviation sigma equals 3. If we draw, by the way, remember X, the X distribution is population. The X bar distribution is the distribution of sample means. If we draw random samples of size 5 from the X distribution, and X bar represents the sample mean, what can we say about the X bar distribution, the distribution of sample means? Okay, is it normal or is it not? And by it, I mean the distribution of sample means. Well, hopefully you can see here that indeed the distribution of sample means, the X bar distribution, will be normal by theorem 1. And it's because of the blue sentence I underlined. Theorem 1 says if the population is normal, the distribution of sample means is normal. Okay? They tell us X has a normal distribution, which automatically means the X bar distribution, the distribution of sample means, is normal as well by theorem number 1. Okay? Let's look at number 2. Suppose the X distribution, talking about population, has a mean mu equals 75 and standard deviation sigma equals 12. But we have no information as to whether or not the X distribution is normal. If we draw samples of size 30 from the X distribution and X bar represents the sample mean, what can we say about the X bar distribution? Okay? Well, looking at this, we have no information as to whether the population distribution, the X distribution, is normal. No information. So theorem 1's out. We don't know that the population's normal. It could be, it could not be. We don't know. But our sample size is greater than or equal to 30. So the distribution of sample means, again, will be normal, but this time it's by theorem 2, or the central limit theorem. Okay? Because we don't know about the population distribution in this case, but since the sample size is greater than or equal to 30, we know the distribution of sample means is normal. Number 3. Suppose you did not know that X had a normal distribution. Would you be justified in saying that the X bar distribution is approximately normal if the sample size was 8? Okay, pause it, give it a shot. What I hope you came up with was a resounding no. It is not known to be normal. And by no, not known to be normal, we are again talking about the X bar distribution. The X bar distribution. It could be normal. We just don't have enough information. Our sample size is not greater than or equal to 30, and we don't know if the population is normal or not. Okay, so hopefully that makes things a little bit clearer. In every problem we want to solve, we first need to determine if the distribution of sample means is normal. We have 2 ways of doing it. Theorem 1, population is normal, so distribution of sample means is normal. Or theorem 2, the distribution of sample means is normal because the sample size is greater than or equal to 30. Okay, that's the first piece of this. So let's put the whole thing together. Again, you do not need to write down this whole problem. I just need you to write down key pieces of information. Folks, you've pretty much learned all the content. You pretty much have learned all the content in 8.2. Now we're going to be seeing what do the examples look like and how do we solve the problems. Okay? So let's solve this one. A certain strain of bacteria occurs in all raw milk. Let X be the bacteria count per milliliter of milk. The health department has found that if the milk is not contaminated, then X has a distribution that is more or less bell-shaped and symmetrical. The mean of the X distribution is mu equals 2,500. Standard deviation is 300. In a large commercial dairy, the health inspector takes 42 random samples of milk per day. At the end of the day, the bacteria count in each of the 42 samples are averaged to obtain a mean of the sample X bar. So first things first, we got to pull key pieces of information out. We want to be able to identify key pieces of information. You might be able to look at this and say, what's the question? I deliberately didn't put up the question that we're going to answer yet because I just want to focus on taking out key pieces of information. So as we do this, I'd recommend you pause the video, you try and figure out the different parts, and then see if your answers match mine. So go ahead and pause the video. See if you can identify the population mean, standard deviation, and sample size. Okay, what is the population mean? Well, according to the prompter, the population mean is 2,500, okay? From the whole X distribution, all of the milk that we're looking at, the given strain of milk or given bacteria count per milliliter of milk is 2,500 on average from the entire population. Standard deviation of the bacteria count is 300. Sample size is 42. Again, we talked about this before. What's the difference between sample size and number of samples? Okay? Sample size, remember, is the amount per sample, and then we have our number of samples. Our sample size here is 42. Our number of samples would be however many days that we count each of the bacteria in the 42 samples. Okay, so make sure you know the difference there. Sample size versus amount of samples. What statistic is being used? Well, remember the difference between statistics and parameters. Parameters tell us info about the population. Statistics tell us info, or statistics are numerical descriptors of the samples. Okay? So what statistic is being used here? Well, they tell us in the 42 samples, we are averaging them to find the sample mean. So the statistic we're using is X bar. In every single, or in the 42 samples, we are finding the average bacteria count. And we can gather that information from the last sentence. 42 samples are averaged to obtain a mean of a sample X bar. So assuming the milk is not contaminated, what is the distribution of X bar? Remember, we want to find the distribution of our sample means. Is that distribution normal? Well, this is the part where we're going to do what we did a little bit earlier. We're going to use our theorems to determine whether the distribution of sample means is normal. If it's not, we're going to stop there and say we can't solve the problem. If neither the central limit theorem nor theorem 1 apply here, we're out of luck. We can't solve the problem. So, looking at this info, they tell me that X has a distribution that is more or less bell-shaped and symmetrical, but they don't explicitly, while bells may be going off in your head saying, hey, that's what a normal distribution looks like, they don't explicitly tell us it's normal. But our sample size is 42. So the central limit theorem can apply here even though we're not sure about theorem 1. We're not sure whether the population's normal or not because they didn't explicitly say it. We would say the distribution of X bar is normal since our sample size is 42. Which we know is greater than or equal to 30. Our distribution of sample means is normal. Well, given that information, what's the mean and standard deviation of the distribution of the sample mean? What they're looking for here is mu of x bar and sigma of x bar. Mu of x bar and sigma of x bar. The mean and the standard deviation of the distribution of sample means. Okay? Well, mu of x bar, we know that since the distributions of sample means is normal, we know that the population mean equals the distribution of sample means. That was our second consequence. Given that our sample size is greater than or equal to 30, our distribution of sample means is normal, which means our mean of our sample means matches our population mean. So mu of x bar will be 2,500. What's our standard deviation? Well, we know our standard deviation of the distribution of sample means is equal to the population standard deviation divided by the square root of the sample size. So I'm doing 300 divided by the square root of 42, which gives us 46.3. 46.3. Okay? Now, what's crazy is I know you might be overwhelmed, like, oh my gosh, we're going through so much content right now, Mr. Carter. I am totally lost. Deep breath. Let's talk about where we're at. Number one, we learned about the central limit theorem, our second theorem. Both of our theorems help us to look at the distribution of sample means. Okay? They both help us to tell, is the distribution of sample means normal? Theorem one was, if the population is normal, the distribution of sample means is normal. Theorem two, if the sample size is greater than or equal to 30, the distribution of sample means is normal. Okay. Then we use those theorems to tell if some examples were normal or not. Now we're solving this problem about milk and we're just identifying information. What's the population mean? What's the population standard deviation? What's the sample size? What are we looking at? Well, we're looking at x bar. We're taking the mean of all of our samples, okay, and making a distribution out of all those samples. We determined if the x bar distribution was normal because of theorem 2, and then we used the consequences of theorem 2. Okay, the distribution of sample means is normal, which means my population mean matches my distribution of sample means mean. And we found the standard deviation for the distribution of our sample means because that's the third consequence of our central limit theorem. And it would be the population standard deviation divided by the square root of our sample size. So what types of questions are we going to answer? Well, assuming the milk is not contaminated, what is the probability that the average bacteria count for one day is between 2350 and 2650? Remember when we worked on this in 8.2 part 1, we looked at, are we looking at a single trout or the average of 5 trout? And that told us whether to look at the population distribution or the distribution of sample means. Here I see they're talking about the average bacteria count for one day, not a single bacteria count. Since we're looking at the average of 42 samples in one day, we're going to be working with the x bar distribution. Well, the good news is we know the x bar distribution is normal because of the central limit theorem. So we're able to use normal CDF, lower bound of 2350, upper bound of 2650. But now I need to find mu of x bar and sigma of x bar since I'm working with the x bar distribution. Well, we just found those in the part above. 2,500 is my mean. My standard deviation is 46.3. And when you solve this, you get an answer of 99.88%. There is a 99.88% chance. And then finally, given the answer above, what's in green, what would your reaction be if the average of the samples on a given day did not fall in this range? Well, think about your answer in the context of the problem. We just discovered that there's a 99.88% chance that out of those 42 samples, if we take an average, of the 42 samples in a day, there's a 99.88% chance that that average falls between 2350 and 2650. So what would our reaction be if the average did not fall in the range? Well, given that there's a 99.88% chance, and consequently only a 0.12% chance that the average didn't fall in the range, because there's a 99.88% chance it does fall in that range, there's only a 0.12% chance it doesn't fall in the range, we would be shocked and we would probably throw the sample out. Since our average should fall in that range over 99% of the time, we'd probably throw out the results for that day and take some significant action. Okay? Guys, thank you for bearing with me. I know this is incredibly difficult. If you feel pretty good, good for you, go on to the practice, okay? But if you don't, what I want you to do, or even if you do, there should be posted a little summary video after this that summarizes all of 8.2. I encourage you to watch it because it'll really help you determine what you need to know. Thanks for your attention. As always, let me know what questions you have.